Now, welcome to Physics Made Easy channel. We are solving NCERT problems, and the last problem that I have solved, in what way is the diffraction from each slit related to the interference pattern in a double slit experiment? And I have explained in details about this. The two slits, they produce interference pattern, and there are two diffraction pattern produced by the single slits, and now both of them combine and we get a diffraction pattern like this, which can be better explained from this diagram. Red color fringes, they are interference fringes, and these blue colored fringes, they are diffraction fringes. Now next part of this problem is part C. When a tiny circular obstacle is placed in the path of light from a distant source, a bright spot is seen at the center of the shadow of the obstacle. Explain why. Again, when a tiny circular obstacle is placed in the path of light from a distant source, a bright spot is seen at the center of the shadow of the obstacle. Explain why. Now, light gets diffracted. Light gets diffracted from the edges. Light gets diffracted from the edges. So I will use this part. This is the circular beam. This is the circular disc, and I will show it its side view. This is the front view or the elevation. For this diagram, I will particularly make use of the side view. So from one side we view the disc as this, and here in the center lies the. Now the beams are coming like this from a distant source. Now these beams are diffracted to the center like this. Some of the beams are diffracted to the center, and we have got shadow like this. This is the obstacle. This is the obstacle, and the shadow that we get is again this, but there is a bright spot in the center. There is a bright spot in the center like this. This bright spot is due to the diffraction of the rays coming from large distance to the center, and this forms a circular pattern. So this was the answer for the question C. Two students are separated by 7 meters. Partition wall in a room of length 10 meters. If both light and sound waves can bend around the obstacles, how is that the students are able to see each other even though they can converse easily? Now, what is this question is? Two students are separated by 7-meter wall. Let us take up this diagram. These are the two students. They are separated by a 7-meter wall. Now they can talk each other, but they cannot see each other, because the basic reason is the wavelength for sound wave, lambda for sound, is large, very large. I mean to say lambda for sound waves is much larger than lambda for light waves. And for diffraction to take place, size of obstacle should be approximately equal to wavelength lambda, or should be comparable with wavelength. Now 7 meters can only be compared with sound waves, wavelength of sound waves, and not with that of wavelength of light waves. You can see velocity of sound in a typical case is 330 meter per second v, and this is equal to wavelength into frequency, and the frequency of the source, you can say you can take any frequency or very smaller frequency. This is 330 kilometer per second, and if you divide it by taking 450, then the wavelength becomes very large, which is comparable with 7 meters. So sound waves can be diffracted with big apertures, and light waves, they can be diffracted only by minute or very small apertures. Now the next case, ray optics is based on the assumption that light travels in straight line. Diffraction effects disproves this assumption, yet ray optics assumption is so commonly used in understanding location and several other properties of images in optical instrument. What is the justification? Now, the important point is diffraction takes place only when the size of the aperture is comparable. I would like to say diffraction takes place only when size of aperture or when wavelength is approximately equal to size of aperture or size of obstacle. But in normal cases, the size of aperture in optical instruments is very large, and we deliberately keep their edges blunt, or we don't take optical instruments with very sharp edges to avoid diffraction. So diffraction effects are negligible, or they are very small. So that's why we can assume that light travels in straight line. So the basic reason is the apertures are very much large as compared to the wavelength of light. Now the next problem or the next issue is this one. Now these are the two tower tops. 18th problem. Two tower tops of two slits are 40 km apart. Like this. The line joining them passes over 50 meter above hill halfway. Between the towers, this is hill halfway, between the towers, what is the longest wavelength of the radio waves that can be sent between the towers without application of diffraction effect? Now this height, this difference is of 50 meters. So we have got the formula for Fresnel distance, df is equal to a square by lambda. Now this 50 meter, we will take this as the size of the aperture. So these 50 meters will be taken as size of the aperture, and df will be taken as this 40. It will be half of the 40, 20 kilometers. So this distance is 20 kilometers. This distance is 20 kilometers. This distance is 20. It means diffraction should not take place for these 20 kilometers. DF, Fresnel distance, should be equal to 20 and the size of the aperture should be equal to 50 meters. Note down, this is kilometers and this is meters. Fill the value and get the answer. Now DF is given to be a square by lambda. A square is 50 meters square by lambda. If I have to calculate lambda, this is a square by df. 50 meter, I will put this value 50 and df is 20 kilometer. 20 kilometers means 20 combined with 3 zeros. So this cancels, this will come out to be 1/8 of meter. 1/8 of meter means it will just come out to be 100 by 8 and it will be 12.5 centimeters. The wavelength of radio waves longer than, if lambda, now if lambda is greater than 12.5 centimeters, then we will meet the requirements. What was the requirement? Diffraction effects will not be effective. Diffraction effect will not be effective if lambda is greater than 12.5 centimeter. If lambda is less than 12.5 centimeter, wavelength of the light is less than 12.5 centimeter, then diffraction effects will be visible. Now the next problem. Next NCERT problem is a parallel beam of light of wavelength 500 nanometer. So this wavelength is given 500 nanometer, falls on a single slit, resulting in diffraction pattern observed on a screen 1 meter away. So this is screen 1 meter away, this is the wavelength. It is observed that the first minima is at a distance of 2.5 mm from the central maxima. Find the width of the slit. Now the condition for minima here is n lambda by this d, size of the aperture. It is first, then it is just lambda by d. So it is just lambda by d. Now lambda by d is theta. We have to calculate the basically width. Now this is theta. Theta on other lines, this is theta. Now what this theta is equal to? Suppose I draw this here a central line. So let me draw a straight line first, otherwise we won't able to understand. So this is this, like this. Now I will draw central maximum. This is the central maximum. This is first minima. This distance is x. This is theta. Theta is x by capital D. Now x by capital D is lambda by small d. X is lambda into capital D by small d. Now this x is given. This d is 1. This d is given. Lambda is also given. And we want to find the size of the slit. It can be found. Size of the slit can be found. And d is the size of the slit. I can write the formula here. D is small, d is equal to lambda capital D divided by x. Now all others are given. You can calculate small d. Rest is very easy calculation which anybody can do. So n has to be taken here 1 because it is the first minima. Now, when two low-flying aircraft passes overhead, we sometimes notice a slight shaking of picture on our TV screens. So just the possible explanation. Now, low-lying aircraft reflects TV signals due to superposition between the directly received signals by the antenna and reflected by aircraft. So there can be superposition. We sometimes notice slight shaking of the picture on TV due to this superposition. It is basically superposition between the rays directly. For example, I will take this as TV antenna, this is TV antenna, and here is the aircraft. This is the aircraft. Now, this is the signal received directly. This is direct signal. Now it receives another signal indirectly. This signal hits the plane first and then gets reflected. It hits here then. Now here superposition takes place. Superposition. And here superposition takes place. This superposition basically is responsible for this, as the low-lying aircraft is moving, so its result will not be stable. Had this been stationary in space, then the image would not have been affected, as it is constantly moving. So this constant movement gives us a varied amplitude here and a varied intensity, and that's why we get an impression that the image is getting shaken. The impression that our eyes get of a shaken image is due to the high velocity of the low moving aircraft, because low moving aircraft does not give us a fixed resultant amplitude. It gives us a varying amplitude that varies with intensity. Next is, as you have learned in the text, the principle of linear superposition of wave displacement is basic to understanding intensity distribution in diffraction pattern and interference pattern. What is justification? Simple justification. Suppose these two waves are coming and they are meeting at this point. Their final displacement will be their vector sum. Displacement is vector, so it will be their vector sum. This is the simple principle, because we take wave nature into consideration, and with waves, instantaneous concept of instantaneous displacement is attached. Displacement is a vector quantity, so there is a vector addition. Simply vector addition of displacement. This is what this principle says. Vectors are added like vectors. Now the last question of this session, which is basically a question based on theory. for wavelength, integral multiple of lambda, for path difference, integral multiple of lambda, we divide, for example, if the path difference is n lambda, we divide the slit in 2n parts. And in this case, corresponding to one part, there exists another part with which it interferes destructively. So that's why in case of diffraction, the condition of integral multiple of lambda, path difference is equal to integral multiple of lambda, is condition of destructive interference. P is equal path difference, I would like to say path difference is equal to n lambda is condition for destructive interference. And the basic reason for this is, for n lambda, we divide the slit into 2n parts, and for every part, there exists another part with which it interferes destructively. So this logic is well explained in theory. See my theory lectures to have a detailed explanation with diagram. And in my next lecture, I will take up NCERT example problem. Until then, just focus on this theory part and give me the explanation of this theory part in the comments, and I will appreciate the correct comments. Thank you very much for being with us for 21 minutes, and I finish this lecture, and we will meet in the next lecture with NCERT exemplar.